So Einstein's general relativity tells us that there are three aspects of warped space-time. There's a warping of space, which we have measured with rather high precision in the solar system already. There's a warping of time, that is, time slows down near massive bodies. That has also been measured with rather high accuracy. And then the third aspect is that the spin of the Earth or the Sun or any other body drags space into motion around itself like the air in a tornado. And that we have never seen in any definitive way. There have been hints of observations of it, but nothing definitive and clean enough to say that you have really seen it, and absolutely nothing that is quantitative. And the principal goal of Gravity Probe B, in my mind, is to see that effect, to measure it with high precision, to verify that the amount of dragging that is created is directly proportional to the spin angular momentum of the central body, to find out what the proportionality constant is. Now, let me explain these three aspects of warped space-time in the context of a black hole, because our goal is to see quantitatively in the solar system and verify general relativity with regard to all three aspects of warped space-time, so that we then can be able to understand definitively how these same phenomena are occurring in the distant universe and doing major things in the distant universe. So I brought my favorite black hole with me. This black hole is actually made out of warped space and time, not out of rubber, despite appearances. So if you take an equatorial slice through that black hole, you might have expected it would have the same geometry as a flat sheet of paper. But in fact, it doesn't. The circumference around that slice would be much smaller than you would expect, or the diameter would be much larger than you would expect based on the circumference. And the next, my first graphic illustrates that. In this first graphic, you see in this trumpet horn shape, it's actually an exact depiction of the warped space around a black hole, the equatorial slice through it. This is as seen by a hyperbeing in hyperspace in which our warped universe is embedded. This is the language a science fiction writer uses. Our universe is curved in hyperspace. You also see two other features here. Well, let me say the horizon of the black hole, the surface is down at the very bottom. It's a circle at the very bottom because I've suppressed one dimension. We're only looking at the equatorial slice. And down near the horizon, the color coding shows red going to black. And this is depicting the warping of time. The flow of time is slowed near the horizon, actually to a halt right at the horizon. As you move back away from the horizon, the rate of flow of time picks up, and that's shown by the colors of the rainbow as you go to the violet very far away. The third aspect of the warping depicted on there is the whirling motion of space around the horizon. Space is moving at a very high clip in the vicinity of the horizon, as indicated by the long white arrow. As you go farther up the cone, or up the trumpet horn, away from the horizon, the angular momentum of space, or angular velocity of space's whirl, gets slower and slower and slower. And in fact, once you're away from the vicinity of the horizon, it is predicted to obey an inverse cube law. The angular velocity of whirl of space goes as the inverse cube of distance from the body, and it's proportional to the spin angular momentum of the body.